and all elements of it to be viewable. Sequences, what are they? A good definition of sequences and a good way to understand sequences may not be the best way. So let me, as I do this, let me try to think of multiple ways of presenting this. We know what functions are. Let's look at kind of a comparison between a special type of sequence, certain type of sequence, and a linear function, and then look at a couple different ways of representing that sequence. Definition: a sequence is a function whose domain is the set of positive integers. How much of this definition do I want to grab? Maybe a lot of this. Maybe that much. So consider the sequence. What sequence? A sub n equals 2n plus 1. Now, instead of giving it a name like F, we give it a name like A. A, B, and C are going to be good names for sequences. Also, U, V, and W. If we're doing this on the graphing calculator, it just chooses to use U, V, and W for names of sequences. Instead of saying f of x, like we would do for a function, we use a subscript, A sub n. So the n represents the independent variable, very much like the x represents the independent variable when we're talking about functions. So if I want the function that first multiplies by a number and then adds 1, I would say f of x equals 2x plus 1. If I want a sequence where I go to a particular term of that sequence, and that term is twice wherever it lies in the sequence plus 1, I would say 2 times n plus 1. To evaluate a function, we say f of 0 equals 2 times 0 plus 1, and we get 1. F of 1 equals 2 times 1 plus 1, and we get 3. We've all been there and done that. For the sequence, we usually don't start at 0. There are some exceptions to this rule, but it says the domain is the set of positive integers, so we begin with 1. So we begin with A sub 1, and if we want to find what A sub 1 is, this is the first term of the sequence. That would be 2 times 1 plus 1. That's 2 plus 1, which is 3. We substitute the number for n, whatever the subscript is, we substitute that for n, and we evaluate that expression just like we would for a function. F of 2 equals 2 times 2 plus 1. 4 plus 1 is 5. A sub 2 equals 2 times 2 plus 1. 4 plus 1 is 5. Now, both of these we could sketch a graph. For the function, we put the x values along the horizontal axis and the function values, which we could also think of as y values, along the vertical axis. And if we're graphing the function, it would look like, let's see, 0, 1, 1, 3, 2, 5. Since it's a linear function, we connect the dots with a straight line. And it looks like that. It goes all the way up there and all the way down there, unless there's some sort of artificial restriction on its domain. For the sequence, we can do a similar sort of thing. If the first term is 3, we can plot the point 1, 3 right there. And if the second term is 5, we can signify that by plotting the point 2, 5 right there. And we can continue upward, but we don't continue downward to the left because we don't plug in 0 for n, we don't plug in -1 for n or -2, and we also don't connect the dots because we don't plug in 1.5 or 1.1 for n. It's only positive integers. So we could very well have a sequence of, well, as many dots working your way up there as you want, but we leave lots of daylight in between the dots, and it only goes one way. It doesn't come back and go to the left. So the graphs of a sequence, the graph of a sequence, the graph of a function look a little bit different. And there's another really good way to represent a sequence, which is maybe more what we think of when we think of a sequence. It's a sequence of numbers, which we call terms. Write it like this: a sub n from n equals 1 to infinity. Kind of just some notation here. A sub n represents an arbitrary term of the sequence, and we allow the n to take on any positive integer value from 1, of course, to positive infinity. We can list the terms. We can't list, if we have a function defined this like this with all real numbers in its domain, we can't list the different numbers in the range. It has all real numbers in its range, and you can say, well, it goes all the way down, it goes all the way up, but we can't list them separated by commas. But the terms of a sequence, we can. We can start with try that again. We can start with the first term, which is 3 in this case. Then there's the second term. Then, what's the third term? It's going to be 7. And the big deal with these sequences is we're going to look for patterns. Where although we love this expression here, a sub n equals 2n plus 1, where if we really needed to know real fast the 100th term of this sequence, we could just plug in 100. Say 2 times 100 is 200 plus 1 is 201. But if we want to generate the first 10 or 15 or 20 terms, we don't want to say, okay, let's plug in 4. 2 times 4 is 8 plus 1 is 9. Plug in 5. 2 times 5 is 10 plus 1 is 11. And just keep doing that. We want to say, 3, 5, 7. What comes next? 9, 11. If we can look at kind of a pattern here, say, from term to term, looks like we're adding 2 each time. This is called defining the sequence recursively, where we can look at a term or maybe a couple of terms and figure out the next term wherever we are in the sequence. What we can say is this: we've got to start somewhere. So let's say a sub 1 is 3. Start with the first term. And then give a set of instructions. If we're at a particular term in the sequence, how do we get the next term? Well, how do we get the next term of this sequence? We add 2. Right? So a sub n equals a sub n minus 1. All right. If I want to know what a sub n is, a sub n minus 1, if this number right there is a sub n, actually it's a sub 1, 2, 3, 4, 5, 6. It's actually a sub 6. But if I'm calling that a sub n, what am I thinking of as a sub n minus 1 in this particular case? If this is a sub n, what and where is a sub n minus 1? The 11 is the term in front. You got the nth term, and the term in front of that is the n minus first term, or the n minus 1th term. No, let's say the n minus first term. That's a sub n minus 1. So I know what a sub n minus 1 is. I want to know what a sub n is. The directions, add 2. I want to know a particular term. We'll look at the term in front of it and add 2. And we just keep adding 2 and adding 2 and adding 2 and adding 2, and that keeps on giving us the next term that we want. So, and this is only valid if n is greater than or equal to 2. We can't use that for the first term. The first term kind of has to be given. We've got to start somewhere, start at 3. And then once we start at 3, then wherever we need to be, we just look at the term in front of it, because there is no term in front of the 3 to look at. But after we get to 3, we just look at the term in front, we add 2, and that gives us. This is called a recursive definition. And it has, it's important if we want to generate a lot of terms in a fast hurry. The recursive definition might be more efficient than the, for lack of a better way to describe this, non-recursive definition. Now, on the final exam, in most cases, not all cases, but in most cases, I'm going to say, give me a non-recursive definition for such and such sequence. Here's a sequence, here's some properties that it has. I need a non-recursive sequence. So if I need the 1,000th term in the sequence, I can just plug in 1,000 for n, and I don't have to add some number 1,000 times in order to figure out what the 1,000 or 999 terms or whatever, to figure out what the 1,000th term is. So let's look at some examples of some sequences. This one, we have a non-recursive definition. A sub n is n times n plus 1 all over 2. Find the first 4 terms of the sequence. There might be a problem on the final exam that's no more challenging than this one. Let's see. A sub 1 is what we get when we take 1 and substitute it for n everywhere we see an n. So 1 times 1 plus 1 all over 2. That's 1 times 2 over 2. And that's 2 over 2, which is 1. So the first term in the sequence, if we want to list them, a sub n equals 1 to infinity. The first term is 1. Second term, a sub 2. 2 times 2 plus 1 all over 2. That's going to be 2 times 3 over 2. That's 6 over 2, which is 3. So the second term is 3. Maybe too soon to start looking for a pattern. A sub 3. 3 times 3 plus 1 all over 2. That's 3 times 4 divided by 2, 12 over 2 equals 6. What's the next term going to be? Whoa. It's going to be 4 times whatever 4 plus 1 is over 2. That's 4 times 5 over 2. And that's 20 over 2, which is, were you thinking 10? 10 for the next term? Now there is a sequence of numbers that we'll probably run into later in this section. Called the, yes.
Oh,
I was going to say called the perfect squares. This is not the perfect squares, but what were you going to say, Miguel?
I was going to say it's like every time it adds 1 to it. So first it is 1 plus 2, or it's 3. Then it goes from 2 to 3, then 3 to 4.
So if we look at the differences, that's 2.
Just adding 1.
That's 2 there. That's 3. That's 4. So we're saying the next one is probably going to be
5, so we go 10.
a 5 there, and then a 6 there, like that. That's what's going on. And there's a nice way to visualize this. Mathematical induction, by the way, for section 12.4, is something that can be used actually to prove this, that this is actually what happens. We can do 5 examples, 10 examples, 100 examples. That doesn't really prove that this is going to happen all the way out for every single example we'd look at. Mathematical induction is a nice way of proving this is actually true for every term of the sequence. There is a sequence that we'll call the perfect squares. These are not perfect squares. They have a different shape. What is the shape of these numbers? You think of triangles? I'm thinking triangles too. I mean, 1 is not all that triangular. I could, make it into a little, triangle? I suppose, if I wanted to. But 3, it doesn't take a whole lot of imagination to get a triangle out of that, right? 3. What about 6? Can we make 6 into a triangle? We'll just add 3 more. All right. How many, aspiring Pro Bowler Tour folks do we have? None. 10? And put 5 dots up underneath this. Still going to be a nice little triangle, a bigger triangle. 6 dots up underneath that. Another triangle. What this formula gives us, if you think about it, is this. This is 1. This is 1 plus 2. This is 1 plus 2 plus 3. This is 1 plus 2 plus 3 plus 4. This formula gives us the sum of the first n positive integers. If we wanted the sum of the first 100 positive integers, 1 plus 2 plus 3 plus 4 plus ... plus 100, that's the 100th term of this sequence. What is the 100th term of this sequence? 100 plus 101 divided by 2. If we divide the 100 by 2, we get 50. 50 times 101, what's 50 times 101? So if you add up the numbers from 1 to 100, the positive integers, from 1 to 100, you get 5,050. So if we had a need to add up the first umpteen thousand positive integers, all we'd have to do is substitute umpteen thousand for n, and we'd have it. Application, kind of a weird application. Long time ago. Oh, it's been 15 years, I guess, since I lived in a place where I could pick up Q108 out of Clarksville, Tennessee. And there was one summer where Q108 was running a special called, well, it was kind of a quiz game called, they called it Hot Summer Trivia. Well, anything to get you to listen to the radio station in addition to the music. Hot Summer Trivia, where it started at $100. And you call in, I don't know, they could take the 8th caller or the 108th caller or whatever, and then on air ask a trivia question, and if you correctly answer the trivia question within like 10 seconds, you win $100. If you don't, the pot builds. And the next trivia question will be worth $200, and then $300 until they get somebody to answer the question. Well, I was listening. I don't think I owned a cell phone at this time. But I was listening in the car, so I wasn't going to participate. But the question was, they got somebody on the line, and it was like a $400 question. And the question was, how many dots are on a pair of dice? 10 seconds. How many dots are on a pair of dice? All together. How many dots? All the the ones and twos and the threes and the fours and the fives and the sixes. Add up all those dots. How many dots on a pair of dots? Is there 10 seconds up? 27. Yeah, the lady on the phone did not correctly answer the question. It was sad. But then for the next person that had a shot at $500, I guess it wasn't so sad. How many dots are on the pair of dice?
42.
It would be 42, right? Because you add up the numbers from 1 to 6, and then you multiply by 2, so it would be 6 times 6 plus 1, and the 2's divide out, and it's 42. 21 dots on a single die. There's our 21. That's 1 plus 2 plus 3 plus 4 plus 5 plus 6. 21 dots on a single die, and then 42 total for the pair of dice. So I'm happy for the next person, whoever it was, that won the $500. But this lady did not win the $400. First 4 terms of this sequence. The key feature of this sequence, in addition to trying to recognize a pattern here, is the -1. Some year, I'll change this. Now, there's no harm in the n-1 because we can take -1 and raise it to whatever integer power we want, but it kind of rubs me the wrong way. So I'm going to change that to n plus 1. It won't change the terms of the sequence at all. But just make that little note there. -1 to the n plus 1. And multiply that by n plus 1 over n. First term. First term, a sub 1 is -1 to the 1 plus 1 times 1 plus 1 over 1. A lot of ones there. It's -1 to the second power times 2 over 1. -1 to the second power is positive 1, so it's 1 times 2, which is 2. If we're listing the terms, and maybe we should, a sub n equals 1 to infinity, the first term is 2. What's the next term? Substitute 2 for n. Wherever there's an n, it's going to be negative 1 to the third power times 3 over 2. What's negative 1 to the third power? Negative 1 times 3 halves equals 3 halves. So 3 halves, whoops, sorry, negative 3 halves. That's kind of the point of this example. Don't want to leave off that negative. Negative 3 halves, let me make it a little bit more prominent, is the next term. A sub 3, negative 1 to the 3 plus 1 times 3 plus 1 over 3. That's negative 1 to the fourth power times 4 thirds, which is 1, times 4 thirds, which is 4 thirds. What is the next term of this sequence? It's really not a recursive definition. We're not allowed to express the numerator of the term in terms of the previous numerator or the denominator in terms of the previous denominator. We have to write it in terms of that term. But we can still figure this out. What's next? Are you thinking negative 5 fourths? And why would it be negative? Because it's an odd power up on that negative 1. So it's negative 1 to the fifth times 5 fourths. It's negative 1 times 5 fourths, and it's negative 5 fourths. So that's the next term. What's the term after that? Positive 6 fifths. What's the term after that? Negative 7 sixths. And so on and so on and so on. All infinity of the terms. When the terms of a sequence like this alternate in sign, positive, negative, positive, negative, positive, negative, all the way through, it's called an alternating sequence. In Calc 2, if you're interested in taking trigonometry, and then Calc 1, and then Calc 2, a whole chapter devoted to sequences and series. And there's an important section in there about alternating sequences and what they converge to, or the conditions under which they converge. When the signs alternate like this, it's called an alternating sequence. And the way to make this happen, a good way, if you're defining the sequence yourself, is to include a negative 1 raised to the power of either n, if you want to start out negative, positive, or maybe the power of n plus 1, if you wanted to go positive, negative, positive, negative. N minus 1 also would have worked, but I just didn't want to raise it to the 0 power. So, not that there would have been a problem with that, I just didn't want to. Example 3, nice example of an application. For the mods, I don't know how nice it's going to be, but a nice example of an application of a recursively defined sequence. So let me go ahead and I guess I can capture just about all of that. Is there more? Just a little bit more. I'm going to capture all that and then see how we can type this into the calculator. Get the calculator to do most of this for us. The population of the winter moth has been modeled by the recursively defined sequence. A sub n represents the population density. Basically, the population density in this case is going to be, I want to say, is it thousands? Yes, thousands of moths per acre during year n. So, if A sub 1 equals A, whatever number A is, that's how many thousand moths there are in this region per acre. Now, to determine how many moths we're expecting there to be the next year, or in a given year, let's say, it would make sense to look at the previous year. Let's say there were A sub n minus 1 moths per acre, well, 1,000 moths per acre the previous year. This particular model says, okay, take that population density of moths, multiply by 2.85, just figuring on how actively they're going to be in the process of reproducing themselves, and then figuring that some of them are going to die, subtract 0.19 times the square of however many there were the previous year. So evidently the death rate is proportional to the square of the population, but the growth rate is only proportional to the actual number of the population. So let's see if we can take this, punch it into the calculator, and use that to predict how many mods there will be in year N. Some calculations here. Now, up to this point, if you press the mode button, everyone see the mode button right next to the second button on the calculator. If you press the mode button on the calculator, up to this point throughout college algebra and all of this course, it's been in function mode. I'm thinking, unless you've just kind of experimented with your calculator to try to get your $110 worth out of it or whatever. You might have experimented with some other modes. If you've taken trigonometry, you might have looked at polar coordinates mode, but it's been in function mode. It's about time to look at a new mode. Let's look at sequence mode. So if you got your calculator, when you press the right arrow 3 times, to go to sequence mode and then press enter, actually highlighting the sequence, so the calculator goes into sequence mode. Now, if you need to graph a function, make sure you know how to put it back into function mode. Just press mode and then function there. So in sequence mode, things look different. If you press the y equals button, whereas you're usually accustomed to seeing y sub 1, y sub 2, y sub 3, instead, it's this. Whoa, kind of different there. There's a u of n. There's a v of n. If we scroll down a little bit, there would be a w of n. Looks like I've kind of got this in here. We kind of got it started. In place of a sub n, we want to use u of n. To display the, well, we're going to need to display the n in a little bit, but let's first type the 2.85. So u of n equals 2.85. If we want to multiply by a sub n minus 1, we want to multiply by u of n minus 1. The u on the calculator is on the 7. If you press the second button followed by the 7, notice the little blue u or yellow u, wherever it is, that will display the u. You want to use parentheses. For the n, the button immediately below the mode button has an x, has a t, has a theta, has an n. That's why I call it the x, t, theta, n button. If you press the x, t, theta, n button in function mode, it displays an x. But if you press the x, t, theta, n button in sequence mode, it displays an n. So you can press that for any n's that you need. Minus 1, close the parentheses. And then minus 0.19. Again, you need the second 7 for the u. Open the parentheses, type the n minus 1 again. And let's see, the n minus 1 needs to be squared. So raise that to the second power. However best your calculator raises something to the second power. The n-min is 1. Basically, that's the starting value of n. For most of our sequences, the starting value of n will be 1. I said the domain of a sequence is a set of positive integers. There are a few applications. Best examples of them we're going to see in this section are financial applications, where you might want to start with an initial value and maybe call that month 0 or year 0. So sometimes n-min has to be changed to 0 if that's the given information. But here it says first year, year 1, it's 1. Well, let's go ahead and do this for 1,000 moths per acre. Well, whoa, shoot, that's not what I meant to say at all. That's first year. That's what that means. I'm so sorry, I just about misled you there. So we're starting in year 1, and in year 1, it's not 1,000 moths per acre, but it's 50 moths per acre. That's what the 0.05. 0.05 thousand means 50 moths per acre during year 1. So let's see, I don't want to go with 15 there. I just want to go with 0.05. Never mind the little set braces around it. If you type it in and then move away from it, the calculator automatically puts them there. I'm really not sure why, but it puts them there. And this is the initial term of the sequence. It's going to start with a 0.05, and then it's going to do a calculation, and we'll see how many moths year 2. Now to do this kind of one at a time, I want to press the second table set up at the top. It's actually on the window button. If you press second followed by window, it takes you here. You want the table start to be on 1, the table increment to be on 1, the independent variable to be on auto, and the dependent variable to be on auto as well, so that it looks like that. And then we should be good to go. Let's see if we can start counting mods. Second button followed by graph. Notice the word table is up above graph. If you press second graph, it will display the number of mods per acre in thousands, year 1. 0.05 thousand, or 50 mods per acre. Year 2, the prediction is that there'll be 142 mods per acre. Year 3, up above 400 mods per acre. Year 4, a little over 1,000. Year 5, almost 3,000 mods per acre. 6, almost 7,000 mods per acre. And by year 7, over 10,000 mods per acre. Growing, growing, growing. But apparently, there can be such a thing as too many mods. So they pull back a little bit, and we're back down to just under 9,000 mods per acre in year 8. But they come back strong in year 9, over 10,000 again, and then back down to just above 9, and then a little over 10, and then above 9 and over 10, and then at some point it kind of starts leveling off. We could look at a graph of this and kind of see what's happening. It's reaching an equilibrium point where there are enough moths where they can continue to reproduce themselves to make sure there are plenty of moths for the next year, but they're not so many that they crowd each other out and take each other's food supply and that sort of thing. So it looks like this is converging to about, 9,700 moths per acre? At least this particular model would predict a number somewhere in the neighborhood of 9,730-something moths per acre long term. A lot of other factors to consider, of course, but that's what this model says. We can change it up a little bit. If I go back to y equals, suppose instead of starting with 50 moths per acre, we start with 10,000 moths per acre. Just drop them there. 10,000 moths per acre. What's going to happen? Well, second table set, I have to go back and restart the table back at 1. So second window, if you want to have that start back at 1. And then second table. If we start with 10,000 moths, it goes down to 9,500. But then it comes back again. And then long term, if you look at it, it's going to settle in again at about 9,730 something moths. That's a comfortable level for that. We want to make sure, though, that we don't do too many moths, because if we begin with as many as 15,000 moths per acre, 15,000, this happens. $15,000 moths per acre in year 1, no moths at all in year 2. The extinction is forever. So, just want to be careful of moth overpopulation there. So according to this model, it looks at the previous year, and based on what it sees in the previous year, makes an estimate of how many moths there'll be in the next year. A really good example, I think, excuse me, of a recursively defined sequence. All right. At some point in the very near future, we're going to need to start adding the terms of a sequence. Summation notation is going to be handy for this. If you're not familiar with this summation notation, sometimes I'll just call it sigma notation because it uses the capital Greek letter sigma to write it out. Typically what we'll have is sigma of an expression. The expression right here may have some i's, some j's, some m's, some n's in it, something to represent the independent variable. That independent variable, it's I in this case, is called, I is called the index of summation. Typically it starts at 1, but it could start anywhere. It could start at 10 or 100 or somewhere in the middle of the sequence. But if we started at 1, basically we say start with the first term of the sequence, or the first value of the independent variable, and then go all the way up to n. So start at 1 and go to 1 to 2 to 3, 4, 5, 6, 7, and go all the way up. Don't stop until you get to n, and then it's okay to stop. Well, each time in this expression a sub I, write down the term. So when I equals 1, substitute 1 for I and write down a sub 1. And then let I equal 2. And when I equals 2, write down a sub 2. And then when I equals 3, write down a sub 3, and keep doing that until you get to a sub n, then stop, and then add all the terms together. The sigma stands for a sum. It means it's not just a sequence with commas in between them, but it's actually the sum of, in this case, finitely many terms. We'll also consider infinite sums of terms of a sequence. The 1 is called the lower limit of summation. The n is called the upper limit of summation. Usually they start at 1, but they don't have to. They can start anywhere and end anywhere. So example 4, we want to write out the terms of the sum and see exactly what numbers we're supposed to add up. And then maybe we'll add them up, or maybe we'll ask the calculator to add them up for us. Did not mean to do that, but close enough. Scoot it back up there. Sigma I equals 1 to 4, so just going to be 4 terms. 1 for I equals 1, I equals 2, I equals 3, and I equals 4. Then we'll stop. But in each case, we want to substitute 1 for I. So it's going to be 1 squared. We'll add 2 squared. Let I be 3 and have 3 squared. Let I equal 4 and have 4 squared. And since we've reached the upper limit of summation, we stop. So it represents the sum of these 4 numbers, which is what? 1 plus 4 plus 9 plus 16, which equals what?
30.
Is that about 30? Now, a couple things we can do with this on the calculator. And there's actually, and you might experiment with this if you're using a newer calculator, and just kind of let me know how it goes. I don't feel comfortable using the sigma notation feature on the calculator because we're still advocating the use of comparatively inexpensive TI-83 pluses in this class. So and they don't have the sigma notation capability. But if you press Math and scroll down there to the summation notation, if your calculator does that, you might play around with it and see if you can get it to come up with that 30 using that type notation. My apologies to TI-83 plus users. If we wanted to do this using the TI-83 plus, we would do something like this. Second list. Notice the stat button. The stat button kind of in the middle of the calculator has the word list up above it. 83s and 84s will both do this. If you press second list and then press the right arrow 2 times, that takes you to the math menu. Once you're at the math menu, you can work your way down to the sum function, where you can find the sum of the terms of a sequence. Thing is, though, then you have to define the sequence. Again, if you press second, followed by stat, or second list, Then press the right arrow just one time. It was 2 times before. It was second list math. This is second list OPS. You'll see the sequence there. It's number 5, just like sum was 5 under the math menu. To find the sum of a sequence. Now's where it gets strange, because on the TI-83 Plus, what you'll see on your screen there is sum, sequence, and it'll look just like that. And what it expects is an expression right there, and a comma, and a variable right there, and another comma, and then a lower limit right there, and then another comma, and then an upper limit right there. And there's actually a place for another delimiter, the increment, but I don't think even the TI-80, the step, yeah. I'll go ahead and put a place for the step as well. Now for the expression, you could use whatever variable that you want. You just have to be consistent with the use of that variable. You could use n, you could use x, you could use I. I'm going to use I because this one uses I. I'm going to type for the expression alpha. Where's the I? It's on the x squared button. I to the second power. That's my expression. So in here I would say I to the second power. And for the variable, I better use that same variable. If that's the one, well, whatever variable is going from 1 to 4, that's what you put in the variable spot. So again, alpha x squared button makes that an I. So in the TI-83 Plus, you just type an I there, and another comma. Don't forget the comma, right up above the 7. The lower limit is 1. The upper limit is 4. And the step is 1. The step, by default, the step is going to be 1 because that's what sigma notation does. If n starts at 1, it automatically increases it to 2 the next iteration, and then 3, and then 4, and then 5. Now the calculator gives you the flexibility if you want to do every other one. You go 1, 3, 5, 7. Or if you want to do 1 in the middle, you could do 1, 1.5, 2, 2.5, 3, 3.5. Sigma notation automatically increments by 1, so the step is 1. So I goes from 1 to 4, and we're just doing a step of 1, and technically I'd need to close the parentheses. So now if I press paste, this is what you would see. You've got sum in front of that, but this is what you would see on the TI-83 Plus, and then maybe close the parentheses one more time for the sum, and press enter, and hopefully it'll just be kind of anticlimactic if it tells me 30 here, but it does. It tells me 30. So it adds them up, yes.
Can you tell me how, like, to do this, how to put the sum and sequence in and all that stuff?
In the Inspire. You're using the Inspire?
Yeah, I can do it the other way, but
Mhm.
when I press, like, when I do the little thing to
Uh-huh.
where I can get it,
Right.
like the little E sign, well, it won't let me put I in there. So
You could use a different variable.
Yeah,
You could
that's
use
what I
maybe
did.
X or N or something like that.
Yeah. But how do you do it the other way, just in case?
I would probably need to look at that after class. Do you have a minute after class? Yeah, let me take just a couple minutes after class and see if I can figure that out, because I really don't know. I'd have to stop and think about it a little bit, but I think I could probably figure it out, and probably should, because more and more students are using the Inspire nowadays. But I don't know exactly, just right off the top of my head. So give me a couple minutes after class, and I would love to explore that with you. The B part, there are just 3 places. It doesn't start at 1; it starts at 3. So we take the 3, substitute that for K, get an answer. Then K goes to 4. We substitute 4. Get an answer. Then K goes to 5. We substitute 5 for K. get an answer. We figure out the value of each of these. 3 squared is 9. 3 times 3 is 9. 9 plus 9 is 18. 18 minus 4 is 14. 4 squared is 16. 3 times 4 is 12. 16 plus 12 is 28. 28 minus 4 is 24. And then 5 squared is 25. 25 plus 15 equals 40. 40 minus 4 is 36. And we added the 24 and the 36 ought to be 60, and 14 is 74. What would have to change if we did this on the calculator? I wonder if it would just let me edit this if I do a second entry. I bet it would. Second entry. I don't have to change the i's to k's. I could leave them i's, but I think I'll change them to k's. Alpha k would be right there. So k squared, if I get off that exponent and then insert a plus 3 alpha k minus 4, there's the expression. And then if I change that I to alpha k, go from not 1 to 4, but 3 to 5, I think that would do it. If my expression is k squared plus 3k minus 4, and the variable is k, and the lower limit is 3, and the upper limit is 5, and the step is 1, this should do it, and it does. It gives us 74. We could do this for a finite. For the sum of a finite sequence, we could do this for a sum of an infinite sequence. If we write the sigma notation, so we're denoting the sum of the terms of the sequence, it's called a series. A series is basically all the terms of the sequence with pluses in between them, and an indication that we should add them up. So the sum of all the terms of a sequence is called a series. If it's finitely many terms, it's called a finite series. If it's infinitely many terms, and it is possible to add up infinitely many non-zero terms and get a finite sum, and if they get small enough fast enough, that would be called an infinite series. The challenge sometimes in pattern recognition is to look at the terms that are given, find a pattern, come up with an expression which expresses each term as a function of some independent variable like I or n or j or k, and then figure out how many there are and write it as using sigma notation. So example 5, the A part actually is, I think, the most challenging example in the section. I think I'll go ahead and start with it anyway, but the others should be easier once we get past that one. 1 plus 4 plus 7 plus 10 plus ... plus 22. If we want an expression for, all right, what variables should we use? There's I, j, k, m, and n typically are the best ones to use here. Which one would you like? I got to vote for n. N, J, K. I guess I heard N first, so I got to go with N. So we want to use N here. So what we want is an expression for the nth term. The nth term. This is not all that trivial unless we notice that the terms, what's the difference between consecutive terms here? 3. Now, when we look at these, we realize these are not multiples of 3. 1 is not, 4 is not, 7 is not, 10 is not, 22 is certainly not a multiple of 3. But we could compare this with a sequence of multiples of 3. What if we compare this with 3 plus 6 plus 9 plus 12 plus ... plus 24? Is it 3?
2.
we got multiples of 3. If I wanted to write this, see if this would make sense. Sigma n equals 1. How many terms are there? If we go from 3 to 24, multiples of 3, there are 8 terms. N equals 1 to 8. And how do I get each term? 1 gives me 3, 2 gives me 6, 3 gives me 9. So n gives me what? So I just want an expression here where if I plug in the n, it gives me a 3 or a 6 or a 9 or a 12 as the output. So if I want to know what's the 8th term, I take that 8 and do what to it to get the 24? Multiply by 3. So how about 3n right there? Would that work? That's not the answer to our problem, but it's the answer to a similar problem, right? A similar problem is good if we can find the answer to a similar problem. Now the answer to our problem, each of these terms is not a multiple of 3, but each of these terms has what relationship to a corresponding multiple of 3? 2 less, yes. Each one is 2 less. So if I want to put in an 8 and get that 22, I should take that 8, I should multiply it by 3, and then subtract 2. Each one of these is 2 less, so I really don't need parentheses if it's just going to be an n there. So how about 3n minus 2? Not a bad idea to enclose that in parentheses, so it's clear 3n minus 2 is the expression that's going from 1 to 8. So we put in 1 for n, 3 times 1 is 3, minus 2 is 1. That's the first term. And then we put in 2 for n, 3 times 2 is 6, 6 minus 2 is 4. That's the second term. Put in 3 for n, 9 minus 2 is 7. So that gives all 8 of these terms, and this expression simply means add them up. Add up these non-multiples of 3. These numbers here, 1 plus 4 plus 7 plus 10 plus dot 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 plus 22, and see what you get. Well, it didn't say to add them, it just said write the expression. Let's look at the B part. 1/9, 1/16, 1/25, all the way to 121st. What's special about these numbers? Fractions, perfect squares. Perfect squares. What variable? We used n. What'd you like? Like k? We use k for this one. Let's use k. We could use k. We want to go from k equals what to k equals what? We want to go to 11. So if we're going to go all the way to 11, we probably should start. Well, the 11 we're going to put in and get this 1 over 121 using that same expression. What's going to give us 1/9? What number? What's the expression? What expression goes right here? 1 over k squared?
Yeah.
All right. So what number can we put in for k to get 1/9? 3. So let's start at 3. Let's go all the way to 11. And I think we'll have 1/9 plus 1/16 plus 1/25 all the way to 1 over 121. Now suppose we didn't like the k, and we also didn't like the fact that we were starting at 3. Suppose instead we want to use j, and we want to start at 1. Sometimes we want to start at 1. How far are we going to go? What's the upper limit in that case? How many terms are there? Well, if we counted these and say this is the first term, second term, third term, which term is this? Is it? Well, it's off by 2, but I think it's off by 2 in the other direction. I want to say it's the 9th term. Is it the 9th term? I think the 9th term of this series is 1/121st. So if instead of using k, going from 3 to 11, we could use j and go from 1 to 9. Since there are 9 terms, it looks like. Well, those 9 terms, 1 over, well, when we put in 1, we need to get 9 in the denominator. So how can we do this? Take the 1, add something maybe, square the result to get 9. Well, we just thought of this as a substitution. It looks like J is K minus 2. So I'm thinking K is J plus 2. Will that work? Put in 1 for J. 1 plus 2 is 3. 3 squared is 9. You get 1/9. Put in 9 for J. 9 plus 2 is 11. 11 squared is 121. You get 1 over 121. All right. Next time, remind me we are halfway through example 5.